Now we're in the second of 4 lessons of the main 4 concepts to learn from calculus. The first one was limits, which we learned in the last couple of weeks. Now we learn derivatives, and we will conclude the last half of this class with integrals or antiderivatives and series. Okay. So this is an introduction lesson, kind of an overview, a big picture idea of what a derivative is. So before we jump into a derivative, let's draw a linear function. Okay. So remember, when you learn linear functions, learn something like a straight line. Let's give this a name, y equals 2x. Remember, a linear function has the form y equals mx plus b, where m is your slope and b is your y-intercept. So in this y equals 2x, 2 is your slope, and there is no plus b, so the y-intercept is just 0. And what does the slope mean? Right, so let me zoom in a bit further. Well, let's write out the points. So we had 0, 0. We also had at point 1, if I plug in x equals 1, 2 times 1, y equals 2. When I plug in 2, 2 times 2, we get 4. Okay, so what's happening? We're going right by 1 unit, and we're going up by 2 units. So this was the idea of rise over run. So the rise was 2 units, the run was 1 unit, so 2 over 1 was our slope. Okay, now in a linear function, to go from 1 comma 2 to 2 comma 4, your rise over run is 2 units. To go from 2 comma 4 to 3 comma 6, your rise over run is still 2 units. So you have the slope of 2 for every single point. So it's easy to calculate. But now the idea of the derivative is, let's make things a little more complicated. Instead of a linear function, which consistently rises at the same rate, what if we take something like a quadratic function? Okay, so let's give it a name. Let's call it y equals x squared. Now you can see that it's not rising at the same rate. Closer to 0, it rises at this rate for positive. It also has a negative slope at this end. But then as we get higher and higher, it rises really, really fast. And the same thing on the negative side. So you can see at every point you have a potentially different slope for a parabola. So how do we calculate a slope for this? And that is the idea of derivatives. Derivatives basically mean rate of change. And in fact, if you calculate the derivative of a linear function, you will get the slope. The slope is a specific example of a derivative. Okay, now let's do a proof by picture kind of idea. So how do we calculate the derivative? There are 2 keywords here. One keyword is a secant line, and another is a tangent line. Secant line is a line through 2 points, and a tangent line is a line through 1 point. And this idea of rise over run, how did we calculate the slope earlier? Slope earlier was y2 minus y1 over x2 minus x1. y2 minus y1 was the rise, x2 over x minus x1 was the run. Okay. So now let me zoom in on that picture of a parabola and let's see if we can guess what's happening here. Okay. So suppose this is my x1 and this is my x2. A secant line will be a line through these 2 points. Aha! And guess what? Well, since this is a straight line, we can still calculate the slope in the same way. So slope here is, let's call this f of x. F of x2 minus f of x1, which is this y2 minus y1, all over x2 minus x1. Now, that's not what we want. We want the slope at x1. We want this value, right? That's only going through 1 point. So what can we do? So let's call this m1, the first slope we took between x1 and x2. Next time though, let's get a little bit closer. Let's call your x2, that's bad color, let's choose another one. Let's call your x2 this point. And now you can calculate another slope, x2 minus x1. That's your m2. Let's take another color and do another slope. Let's move the x2 even closer and calculate another slope. And you see what's happening? We're still going through 2 points, but we're getting closer and closer and closer to that blue line, right? And once we get really, really close to the blue line, what happens is that secant line, a line through 2 points, will really become a tangent line, a line through 1 point. So the official formula here is, let me redraw that parabola. Let's call that x1 a value, let's say a. So the derivative of a, derivative at a, is basically we go to the right h units and we shrink that. We try to get that h as close to 0. So the derivative f prime at a, that's the derivative notation prime, is given by f of a plus, you go to the right a little bit, right, that's your f of x2, minus f of x1 is just at the point a, all over h. H is the difference between x2 minus x1. But we also do one thing. We let that h be closer and closer to 0. So we are really taking the limit, which we learned from the last section. Limit as h approaches 0. And so folks, here it is. This is the derivative, f prime of a. That's the official definition of the derivative. It's basically a slope. It's the rate of change or the slope at a certain point. And now you see, at this point a, the derivative will be different than this point a, or this point a, or this point a. And if we just do this limit and this calculate this fraction, we will get our slope. Anyway, that's the answer. Next time we'll compute a little bit of these derivatives with this definition, and then I'll show you some tricks as we complete this section.